Hello everyone, this is Group 19. We are the Automated Digital Microfluidics Workstation. I'm Caleb.
I'm Craig.
I'm Jen. Our sponsors for this project are the Oregon State University Department of Chemistry.
We'd like to say a big thank you to Myra Costa Jojo, Arnie Bostrom, Sam House, Donald Tier, David Mandrell.
Upon successful completion of all of our engineering requirements and our customer requirements, we will be providing the system for use in the chemistry department.
Thanks for watching. In this video, Craig will be giving you an introduction and brief explanation of our project. Jen will go through the block diagram. I will talk about our unique design aspects. We will give you a project demonstration, and then all three of us will leave tips for next year's seniors.
We are Group 19, and we're doing an automated digital microfluidics workstation that uses the principle of electrowetting on dielectric. Digital microfluidics is a technology for lab-on-a-chip systems based upon the manipulation of discrete droplets by transporting, mixing, and storing fluids using a standard set of basic instructions. Electrowetting on dielectric is the modification of the wetting property of a surface with an applied electric field due to the change in solid electrolyte contact angle due to a potential difference between the solid and the electrolyte. We create an electric field by varying potentials on adjacent electrodes on a work surface. The Young-Lippmann equation describes the behavior of a drop on a work surface. What this equation tells us is that by changing a voltage, we can change the contact angle of an electrolyte with respect to the surface. Graphically, this is displayed here. So in the top picture, we have a droplet of water with a large contact angle, which has no potential difference. When you apply a potential difference, the water spreads out and creates a smaller contact angle. In step 1, both pads have the same potential. In step 2, the red pad is brought to ground, changing the contact angle of the leading edge, but not the back edge. This is due to a differing strength of the electric field on the sides of the drop. With differing angles, we have differing surface tensions, as you can see here, and thus differing forces on the drop. The drop moves until the surface tension is balanced, as it is in Figure 3. Through the manipulation of voltage to an array of electrodes, drops can be moved on a work surface. With this functionality, mixing of different fluids can be performed.
The basic block diagram for the digital microfluidic system is displayed here. The power supply plugs into a standard wall outlet and includes an AC to DC conversion, a voltage step down to supply the low power electronics of the system, and a voltage step up used to create the electric field at the work surface. It provides a 3.3 volt rail, a 15 volt rail, and a 700 volt rail. The microcontroller block is used to control the switchboard. It is equipped with programs that provide droplet mixing and movement functionality and is user programmable as further applications arise. The switchboard is what controls the voltages to the work surface. It accomplishes this through high voltage MOSFETs, which are turned on and off as needed by the microcontroller. The work surface is comprised of copper electrodes under a hydrophobic dielectric material which facilitates the droplet motion.
In this section, I will be discussing our project's unique design considerations. These considerations will cover the boost converter, the high voltage switchboards, the non-isolating buck converter, and the work surface. Our single bulb boost converter changed quite a bit from fall term design to winter term implementation. We were unable to find an integrated circuit solution for our boost requirements. So we decided to make it out of passive components of switching FETs, inductors, and resistors. The big issue we ran into with this block was the limitation of current versus inductance. We ended up finding two 160 millihenry inductors that were rated for 500 milliamps apiece. They ended up working quite well, as our block didn't need more than 300 milliamps. Another issue we came across was the price of capacitance as voltage increases. Our 1000 volt capacitor was only rated to 1 microfarad and cost nearly $15. While this is not a lot of money in the grand scheme of things, it was a lot on our budget. Finally, we came across the SG3525A PWM generator. This is an excellent choice to generate our switching signal, as it has a switching frequency range from 60 kHz to 400 kHz and a duty ratio of 0 to 49% or 51 to 100%. Because of size limitations in our project, we really wanted to get as many parts on PCBs as possible. One of these blocks was the high voltage switchboards. These boards implemented two cascaded inverting topologies for an overall non-inverting input versus output. The big issue with this board and the big size hampering on this board was the SMD resistors. I was unable to find any resistors that could handle more than 500 volts apiece. I was pretty surprised. So I was forced to take two of these SMD resistors and wire them in series so they could drop 1000 volts safely. Unfortunately, the size of the resistors was roughly 10 millimeters by 5 millimeters, so they took up quite a bit of real estate. Because of this, I was only able to get one board to switch 7 channels. It was still an improvement on size, but inefficient. For the buck converter, Jen was able to find a non-isolating chip that worked out quite well. This chip was commonly used in washing machines and ovens and other high voltage household appliances. It is able to take an input of 180 to 360 volts DC and output a 15 volt 350 milliamp channel and a 5 volt 200 milliamp channel. In the end, this is the only way we were able to get our voltage requirements of 1000 volts and 15 and 5 volts out of one power supply. Finally, the work chip ended up being the most challenging block of all, as we were really not able to complete it fully. We tried several methods to build this chip, including photolithography, toner transfer etching, hand-cut copper tape, and laser-cut copper tape. We ended up settling on the laser-cut copper tape. David Mandrell at MBI was able to whip up a few SolidWorks sketches, and we were able to tape large chunks of copper to a PET substrate and cut them out.
That left side.
These are our tips for future seniors. Anticipate spending a lot of time on this project. It's much bigger than a 2-credit hour class.
Also, I recommend taking the time during Christmas break to build your project because integration is going to take much more time than you think.
Check your data sheets for ratings. If you're looking for something that can handle current, make sure you check the voltage because it'll always get you. Good luck.
So,
Is that okay?
yes, sir.